Hello students, how are you? I, Professor Prasant Bua, Dr. Subhash Technical Campus, Junagadh. I hope you will understand all previous 3 lectures related to earthquake resistance of building. Subject is design of reinforced concrete structure offered in 7th SEM Gujarat Technical University Civil Engineering branch. So in this lecture, it means series of lecture 4, we will still continue the earthquake resistance building remaining portion, and in this lecture we will discuss about very important points while twisting of building, or the another important point is design capacity of building, what should be the design moderate and ductility of building, what should be the flexible building and stiffness building. So in previous 3 lecture we will similar the philosophy should be discussed. In this lecture 4, we will discuss about the design capacity concept, what is the twisting moment. So start with first, what is the twisting moment on building and how it should be occur. So we continue with the 3 lectures related to earthquake. So all of you have understand the basic of earthquake resistant structures. So there are the earthquake resistant structure have 4 varieties, namely lateral strength, adequate stiffness, good ductility and good structural configuration. These 4 are the main key point to resist the building against the earthquake force. Out of these 4, we already discussed about the lateral strength, how we achieve the lateral strength. The 4th one we also discussed good construction configuration, how we decide the shape and size of the building, we will discuss in our lecture 3. Same, the lateral strength that will be discussed in lecture 2. So today we will discuss about the good ductility and adequate stiffener of this earthquake resisting force. So start with the twisting of building. How building twist during the earthquakes. So why building should be twist? First, that question should be arise in your mind. So I will start with one example of common you have to feel, and you have to realize this example at every in your childhood. So if your childhood you must be have sit on rope swing, a wooden cradle tie with the coir ropes to the studded branch of the old trees, and the more modern version of this swing can be seen today in a children's park in a urban area. So they have plastic cradle tie with the steel chain to steel framework in a modern era. So consider a rope swing that tied identically with 2 equal ropes that usually we have to notice. It swing equally when you sit in the middle of this cradle. All of you have to feel this phenomena. If we have to sit properly in the middle of cradle, your swing should be properly done. If you have to nearby the any of corner in a cradle, your swing should be not properly swinging. It should be arise a twist, or it may be inclined towards the direction. So the building too are like this rope swing. So just they have our inward swing. So the vertical wall and column are like rope. So in our building, what should be we have to take as a swing? So vertical member, it should be a wall also, or it should be a column also. So these are the our swing we can use for the wall and column. So that floor I like cradle. What should be our cradle? It's our floor, or you can say the slab. So the building vibrate back and forth during the earthquakes. Building with more than 1 story are like rope swing with more than 1 cradle. Now you have to visualize the single story has a single cradle. So if the multi-story building, so you have to visualize the swing with the different cradle at different story height. Now what should be the phenomena occurs during this twisting during earthquake? That will be seen in our figure 1. You can see that ideal condition of cradle or swing you have to notice. Generally in old era we have the string with the any particular wooden string, and it should be attached with the 2 string, and this one is the cradle. Now you have to sit on middle part. Your swing should be properly without any twisting direction. Now you have to move over the any corner near about left or right. Your swing should be start with the inclination. Like same, our multi-story building, so there are the number of cradle you have to locate it. So this is the example of single story building, and this is the example of multi-story building. So this is the single story building, this is the 3-story building. So the rope swing on the buildings, both the swing back and forth one shake horizontal. The former are used from the top, while the latter are rise from the ground. So these are the comparison with the single story and multi-story with the example of the cradle that you have to already notice in your childhood. Now what should be the happen? So thus, if the C for the sky, a building with identical vertical member and then are uniformly placed into the two horizontal direction. When second is to be based the certain direction during the earthquake, swing back and forth such that all the points of floor move horizontally by the same amount in the direction which is shake. That will be seen in figure 2. Now you can see that ideally vertical member should be placed. You can see in this plan. And uniformly planned building cause all the point on the floor move the same. Now we located the identical vertical member is like a column, and this is the uniform floor that should be maintained. Now you can see the earthquake movement direction. It should be the same direction of swing, and now all the vertical member are identically performed very well. But during this earthquake shaking, it may be not vertically properly, and certain this direction it should be create to chance the twisting of our building. How? We will see in this next slide. Again, let us go the rope swing on a tree. If you sit one end of the cradle, it should be twisting. Now move more on the side of your sitting. This also happens sometime when more your friends bunch together in sit one side of the swing. Now you have to sit that one or two person again sit the same cradle. Again it should be a chance to the twisting. Likewise, the mass of the floor building is more than one side. Now we cannot stable the equal floor in particular story. Now at any corner or any joints, the mass should be heavier compared to throughout the building floor. Then what should be the happen? Instead of one side of building may have storage a library. Then that side of building move for more under the ground of this moment of shaking. Now this building moves such that floor displacement horizontally as well as it should be try to rotate, and that will be a very dangerous effect during the earthquake. Now I should say the word about library. Means one story, one boys hostel should be constructed. Among the part of one building, we should construct that library. Will full store with the books and equipment and furniture, all that set. So at the portion of that building particular, the mass should be act heavier compared to the rest of floor. So it should be twist to the try to twist over that particular mass, and that should be avoided to resisting this twisting moment. How? We will see in this figure 3. You can see. Now same example of cradle or swing, you have to notice that. Now person you have sit nearer to the rope, it should be not swinging properly. It should be try to twist in the direction of mass. Same you can see that this is the light side of building and this is the heavier side of building. Now earthquake move in horizontal direction, that the heavier side of building it try to the twist, and it should be the separation over the lighter and heavier span particular this plan. So we avoid the ununiformity of mass in a plan while we analysis or design particular building as well as we create the plan. So even if vertical member are placed uniformly in plan of building, more than mass on one side cause the floor to twist. It's not about the verticality member uniformity. It's always in this building, it's also vertical member are uniformly distributed, but our mass is not distributed throughout the span. So at any particular plan that you have to design, or it should be a analysis, there are the uniformly equally mass should be distributed throughout the plan, so that these twisting moments are not occur while the earthquake should be occur and the ground should be shake in horizontal direction. So this all about the twisting moment. You have to remember with the example of swinging, so you can visualize how the building should be twist under the motion of horizontal. Now, what twist does to building in a members? So twist in a building called technical word we have called as a torsion by the engineers. So make the different portion at the same floor level move horizontal by the different amount. It depends directly on the particular member mass, and this include more damage in a column as well as wall, because we all know that our same example you have to visualize the swinging. If that horizontal motion are not properly, then our swing it should be break. So in our case of building, what should be the inside of swing is nothing but our wall and column. So there are the major chance to damage under this twisting moment. Many of building may have been severely affected by this excessive torsional behavior during the past earthquake that will be seen in our lecture 3. I seen one photograph. In particular, the middle of the building separation should be done. So this is nothing but this twisting or torsional effect. So it is the best minimize if completely avoid this twisting by ensuring the building have symmetric in plan. So that's why we not go further about the any shape that building it should not be symmetry in plan. We always try to plan in symmetry. So the distribution mass and uniformly paced vertical member will be undergoes this symmetry of plan. If the twisting moment cannot be avoided, special calculation need be done to account for this additional shear force. Now, in case of our building criteria, we note a significant effect of this twisting moment. So in that particular case, we specially calculation this twisting amount force, and opposite of this twisting force means our lighter side of building we should construct at the shear force. So the mass should be balanced and we have to nullify the twisting effect. So the design of building, the design seismic code IS 1893 2002 has a provisional for such type of calculation. How we calculate shear force in building, that should be also in our study part. How we calculate the shear force in building in numerical we also discuss using this code how it should be calculated. But for the sure building with the twist will perform poorly during the strong earthquake shaking, and this effect we have to nullify in our building. Why and how? So use the use of IS 1893 2002 earthquake resistance code. Now what is the seismic design philosophy of building? So the earthquake resistance building, to resist this earthquake, we have the some philosophy of design criteria that should be created observed by the past decade of major earthquakes. So the engineer do not attempt to make earthquake proof building. That will be repeatedly I focus on this word up to the starting lecture 1. We cannot provide earthquake proof building. We have to try just earthquake resistant building. So will not get the damage even during the rare but strong earthquake. Such building will too robust and also too expensive. So the instead of engineer intensive, the make building earthquake resistant, such a building resistance the effect of ground shaking, although they may get damaged severely but would not be collapsed during the strong earthquake. We allowed severely sometimes of damage, but total our structural elements are not collapsed during the rare but strong earthquake. Thus, the safety of peoples and the content ensuring the earthquake resistance building. Thereby, the disaster is avoided. And this is the major objective of seismic design code throughout the world. Why we have seismic design code is introducing, and why we have compulsory after the 2001 earthquake, because we have to get the measure, avoid the major disaster in a building. So our major objective to use this code for throughout the world, the seismic design is properly to resist this type of natural phenomena occurs like earthquake, tsunami, etc. So what are the seismic design philosophy we have calculated? So the earthquake design philosophy may be summarized as the following. First and foremost criteria is under minor but frequently shaking, the main member of building that carry vertical and horizontal force should not be damaged. However, the building parts that do not carry the load may sustain repairable damage. So our main element of building like vertical and horizontal force should not be damaged during this sacking. Hence, all our building should be maintained. So for this vertical load and horizontal force resisting, we already discussed in previous 3 lectures what should be done to resist more vertical and horizontal force. Second point, under the moderate but oscillation sacking. First point is under frequently sacking. Second one is under moderate sacking. The main member may sustain repairable damage while the other parts of building may be damaged such they may have even to replace after the earthquake. So we have allowed in moderate sacking. But our main part should be repairable and the minor, or you can say the rest of building are replaced with the new one. And third point, under the strong but rare sacking, the main member may be sustained severe. Even the replacement should be done after the damage, but the building should not be collapsed. So under these 3 criteria, our design philosophy occur while the building should be designed earthquake resisting building. Now we will, this all 3 cases we have effect during the earthquake shaking will show our understanding by one figure. You can see the first criteria, minor shaking. You can see that our vertical member is safe. There are the no crack are visualized of vertical and you can say that floor slab. But yes, of course we have the damage of our masonry. We should be allowed during this first case, but we should not allow the cracking in our main part. Now moderate shaking. So that frequently shake should be high. You can see that minor of my horizontal portion should be affected with earthquake. Still, our vertical member should not damage and somehow the masonry should be totally collapsed, so we have to replace that. That should be allowed in moderate shaking as per the IS provision. Now strong shaking and the rare earthquake. Our horizontal member is also collapsed. Our masonry is also damaged, we have to replace with, but still our building are not collapsed. So these are the important of vertical member and the joint between horizontal and vertical member. How should we create the joint like that? In under strong shaking, our building it should not be collapsed. So under this 3 case, our building should be identified. Either our building is under moderate shaking, minor shaking or strong shaking. Likewise, we analyze or design the earthquake resisting code so that our building is not intensively so costly that should be not affordable of client. So the performance objective under the difference intensive of earthquake shaking are represented with these 3 criteria under minor, moderate and strong. Now damage in building unavoidable. Which type of damage should be unavoidable? It not be avoidable while the case of earthquake. So the design in building to resist the earthquake involves controlling the damage to accept the level of reasonable cost. So the common thinking that crack of building after the earthquake means the building is unsafe or habitation of engineer designing this earthquake resistance building recognize that some damage is unavoidable. So the different types of damage mainly visualized through the crack, especially so the concrete and masonry of building occur in buildings during the earthquake. So some of these crack are acceptable while the other are not. So that should be inspection after the earthquake should be occur. So which type of crack should be generated in building? Either your crack should be in a masonry or either your crack should be in concrete work, your vertical member, your horizontal member. So somehow the crack should be acceptable, but some are not. So that not acceptable crack, you have to strengthening that crack or you can replace that element also if the crack is severe. So from the instant in a reinforced concrete frame building with masonry filler wall between column, the crack between vertical column and masonry filler wall are accepted. But the diagonal cracks running throughout the column are not. That should be a very dangerous in a building. So in a general, qualified technical professionals are knowledgeable for this case and severity of damage in earthquake resistance building. So after the earthquake should be occur, there are the team to inspect your building and he have to analyze this under moderate, minor and strong. What should be the crack should be acceptable and which are not. Same here you have to see the diagonal crack. These are the very dangerous in the column if you have to perform the diagonal crack, or you can say the X crack. So this crack in column or vertical load carrying capacity of building should be damaged, and your load hierarchy system to floor, beam, beam to column, and column to again foundation, it should be break with this phenomena of X crack. Then it should be permanently remove this column, or you can say if the crack is minor, so we also strengthening the column. So it depends on which type of cracks and how it should be remedial measure as per the IS code is suggest. That should be done after the inspection of this building. Now acceptable damage of ductility. Now what should be the ductility and what should be the acceptable damage? So that task now is identified to acceptable form of damage and desirable building behavior during the earthquake. So to do this, let first understand how the different material behave. So like some material are behave in elastic form, some material behavior plastic form, somehow elastoplastic, compact, semi-compact. So considering the white chalk, use the write on a blackboard, and steel pin with solid head used to hold in a sheets of paper together. Yes, a chalk break easily because they have elastic. On the other side, steel pin allow it to be bent back and forth. So engineer defined to properly that allow the steel pin to bend back and forth by the large amount as ductility. Chalk is, again I say, it should be brittle material, so we not acceptable damage under the chalk like brittle material. So the earthquake resistance building, particular their main elements need to be built with the ductility in them. Such building have to ability or sway back and forth during the earthquake. What should be the effect of back during the earthquake? It should be shake. After the earthquake, motion should be stopped. That building should be get in original position. In technical, it should be treated as back and forth during the earthquake. So to the withstand of earthquake effect with the same damage but without collapse, that will be seen in figure 3. So the ductility is one of the most important factor affecting all building to perform under the earthquake. So in simply, ductility is a capacity of building like material, structure, system, element or member undergoes a large deformation with significant loss of strength. And the another aspect of ductility you can also say is nothing but our stiffness. So in terms of technical, you can also note down ductility is equal to ultimate displacement at collapse divided by yield displacement in first damage. So you have to directly notice which type of ductility it should be done in particular your building itself. Now how to make building ductile for a good seismic performance. Now again raise your mind, if ductility is good, then how it should be improved in our building. So in different construction material, different parts of building, that all performance of ductility are different phenomena. So the first we have to check our construction material. So in Indian, most and non-urban buildings are made in a masonry. So in plain, masonry is generally made by bunt of clay brick or cement mortar. However, in hilly area, stone may be used as a masonry with mud mortar and mud prevented. But in recent time, it should be being replaced with the cement mortar. So masonry can carry the loads and that cause the compression. So pressing together, but can hardly take the load causes of this tension. So we all know that masonry is made by brick and mortar. So it should be enough to resist the compression. You can see in our first slide. It should be carry the compression force of any particular masonry. But they have not performed under the tension load. You can see that our joint should be created as a crack. So that should be avoided for in case of ductility. So the concrete in another material that has been properly used in building construct particular over the last 4 decades. So the cement concrete, it made of crushed stone pieces called aggregate. Another particles is sand, cement and water mix is appropriate proportional. So the concrete is much more stronger than masonry under the compressive load. but again its behavior in a tension is poor. So the property of concrete critically depends on amount of water used in a making concrete. The second is too much and too little water. Both the case are havoc in case of concrete. In general, both the masonry and concrete are brittle and fail suddenly. So what should be the done? So we can use steel in a masonry or concrete building as a reinforcement bar of the diameter ranging from 6 to 40. It depends on how the thickness of masonry should be done. So reinforcing the steel can carry both tensile as well as compressive load. Moreover, the steel is also, we know that the ductile material, that I see the example of steel mill and choke. So this important property of ductility enables to steel bar to undergo the large elongation before breaking. So concrete is used the building along with the steel reinforcement bar, and hence the composite material is called reinforced cement concrete, simply RCC elements. It should be resist both the case compression as well as tension. Now capacity design concept. This one is very important while we have to design a earthquake resistant building. What is capacity design concept? So let us know two bar for the same length and cross sectional area, one made by ductile material and another of by brittle material. Same length, how to choose two bar? One is made by ductile material and another made by brittle material. Now pull these two bar until they break. You already notice that ductile bar elongate and by large amount before its break, while the brittle bar are break suddenly on reaching its maximum strength. So a relatively small elongation amongst the material used in a building construction. Steel is ductile while masonry and concrete are brittle. That will be seen in our next figure. You can see the tension test of material in case of ductility. The first is bar of force F. You can see in vertical. This is the bar force at F. This is the elongation bar. Now the ductile material, what should be the focus? It should be try to get the maximum force. After it should be resisting the maximum force. It start to the elongation. Now in case of elongation bar, you can see that force, maximum force. After that it should be elongate. It should be breaking point. So while we made by the steel or brittle material, that you have to see this breaking force, and the same bar but our material is ductile, you can see that visualize of breaking force. There are the vast difference of elongation. So what should be the advantage of elongation? That question should be arise in your mind. So that elongation should be done, so it means our building is more resisting this force, and of course it gives the sign before breaking. So we have to avoid the people damage, or you can say the building damage during this such kind of rare earthquake should be done. So our material should be, of course, raising the design of ductility material, and the concept name is capacity design concept. It means we have not totally building under the ductile material, but at the position where the board ductility is important, that parts or that member should be under the ductile material, and the concept is known as capacity design concept. It's very useful and important as exam aspect, or you can say the earthquake resistance phenomena is also important, this concept. So this is the tension test of material, ductile versus brittle material. Now let us making the chain with link made by the brittle and ductile material. Another, I get the second example of one chain have some link of chain are brittle and some link of chain are ductile. So each of this link will fail just like a bar shown in figure 2. Now hold the last link at the either end of the chain is apply force F, since same force F being transferred to all the link. The force in each link is same. So as more and more force is applied, eventually the chain will break when the weakest link is first break. So if the ductile link we should provide weak one, then it should be resist more load and it should be large finally elongation. So instead of brittle link is weak one, then should be chain which fell suddenly and so small final elongation. Therefore, if we want to have such ductile change, that we have to make ductility link to the weakest link. So we have to not design all over the ductility link. We have to replace weaker link with the ductile. So it should be rigid, large elongation during this force should be rigid. You can see the original change. Okay, so now the brittle, all the brittle link are there, and you have to pull out this force, then it should be break. Where it should be break is middle one. So after the middle link, I will be replaced with the ductility link. So it should be rigid, large elongation under the this load chain. You can again see after the replacing of this ductility chain, it should be elongation are large. So just put out one link and the load carrying capacity is increased. The same material, rest of this material are same, brittle. You can see in this figure. So this is nothing but design chain criteria, or you can say the design capacity of building. So just we have to replace with the ductility part where it should be important under the pull out or tension test during the earthquake. So now earthquake resistance design of building, we have to go forward that earthquake resistance building itself. So design like the ductile change, for the example considering the common urban residential apartment of construction, the multi-story building made of reinforcement concrete. It consists the horizontal and vertical member, namely we have to take as a beam and column should be constructed. The seismic inertia force that will be seen in our lecture 2 generate at the floor level and transfer through the various beam and column through the ground. That should be our load hierarchy system. So the correct building of component needs to be made ductile. So the failure of column can be affect the stability of the building, but the failure of beam localize the effect, and therefore it is the better to make beam be ductile, weak link should be column, and this design of RC building is called strong column weak beam design. So this is the major word while you have to design of earthquake resistance building. Again I repeat, strong column weak beam, because our beam is horizontal direction, so it self resist to horizontal force, but our alignment of column is vertical, so it need to strong during this earthquake force, while beam is weak. So we saving the material in beam. On that other side we have to enough strong of column design. So this is the concept of strong column weak beam after the revision of IS 1893-2002. This column, this concept should be created. What should be done in previous time? You have to see in that strong column weak beam. Nowadays this design should be earthquake resistance design, and it should be more effective, should be tested during the earthquake. You can see that column size, it should be strong. You can visualize the beam side, it should be weak. Now what should be the rational method? We have to perform during the past decade. What should be the method? Column are weak and beam should be heavier. There are the inversely proportional of this design. We didn't require about the heavy beam, but what should be the required? Heavy column. Instead the shaking of earthquake should be done. So these are the reinforced concrete building design, and the concept itself, strong column weak beam. That is the very important theory. It should be asked in GTU exam also, practical viva also, and when you have to start any preparation of GPSC, there are the most of question are related to strong column weak beam. What is the concept behind that? That should be very important things. Now quality control in construction. So the capacity of design concept in earthquake resistance design of building with fail of this strength. So the strength brittle construction material like masonry, concrete is highly sensitive to quality of the construction material. Again there are depends on workmanship, supervision, construction method that we have to use. Similarly special care is needed to construct the ensure that the element match the ductile and intend to provide with the features that should be adequate with the ductility. Just we have to design a building in a paper, it should be ductile, it's not okay with the field. There are the lots of error done in a field. The poor workmanship are important role play. Supervision is less, then it should be avoid the ductility, and construction method that will be used on a field. That are all the three criteria is very important to maintain this quality control. So the regular testing of construction material and qualified laboratories are periodic training for the workmen or professional training house on the site evaluate the technical work element for good quality control, and that's why our quality control department have checked the high-rise building as well as the important building while it should be register this natural phenomena force or not. So that's thank you friends. This all about the lecture 4. What is the design capacity concept? What should be the criteria to register? Masonry should be strong enough. What are the 3 main criteria for checking under minor, moderate and severe? And third most important, what is the twisting and torsion moment during the earthquake should be occur in a building. So thank you students. If you have any doubt, write in our comment box in my YouTube channel. In next lecture we will again continue about which are the design criteria of earthquake resistance building. Thank you friends.